Today we're going to investigate the role of a in y equals ax squared. To do this, we're going to graph y equals x squared, y equals 2x squared, and y equals 5x squared, using the table of values shown here. So I've started the first ones for you. So for y equals x squared, if I take negative 3 and square it, that's going to give us positive 9. For 2x squared, following order of operations, negative 3 squared is 9. 9 times 2 is 18. And for 5x squared, again following order of operations, negative 3 squared is 9. 9 times 5 equals 45. So take a moment now, pause the video, and complete each table of values. Now that we have the table of values, we can graph each of the following quadratics. So starting with y equals x squared, I'm going to graph that in blue. Next, I'm going to graph y equals 2x squared in red. And finally, I'm going to graph y equals 5x squared in green. Compared to y equals x squared, what happens to the y coordinates of y equals 2x squared and y equals 5x squared? If we compare the y values of y equals x squared and y equals 2x squared, we see that all the y values are 2 times greater. Similarly, if we compared y equals x squared to y equals 5x squared, we see that all the y values are 5 times greater. So we can conclude that, compared to y equals x squared, the y coordinates of y equals ax squared are a times greater. Again, a is the number in front of the x squared. Where would you expect the graph of y equals 3x squared to appear relative to the 3 graphs we have here? Well, since 3 is between 2 and 5, a good guess would to say that would be somewhere between the graphs of y equals 2x squared and y equals 5x squared. So between y equals 2x squared and y equals 5x squared. Let's look at what happens when we change our a values into fractions, less than 1. So again, let's complete the table of values. First, pause the video and try this yourself, and then come back and check your answers. So negative 3 squared will give us positive 9. 1/2 of 3 squared, that's negative 3 times negative 3, which is 9, and half of 9 is 4.5. And 1/4 3 squared, that is negative 3 squared, which is 9, and 1/4 of 9 is 2.25. Here are your y values. Same as above, let's graph each of these. I'm going to graph y equals x squared in blue. Y equals 1/2 x squared in red. And finally, y equals 1/4 x squared in green. So there are my 3 graphs. Compared to y equals x squared, what happens to the y coordinates of y equals 1/2 x squared and y equals 1/4 x squared? So same as above, if we look closely at the y coordinates, we see that starting with y equals x squared, all these coordinates for y equals 1/2 x squared are 1/2 of those from y equals x squared. And comparing it to y equals 1/4 x squared, they're all 1/4 the values of y equals x squared, or just divide them all by 4. So same as above, we can conclude that compared to y equals x squared, the y coordinates of y equals ax squared are a times the value of y equals x squared. Where would you expect the graph of y equals 3/4 x squared to be? Well, 3/4 is greater than a half. It's definitely greater than a quarter. So 3/4 should be somewhere in between y equals x squared and y equals 1/2 x squared, because 3/4 is less than 1 but greater than a half. So we can say between y equals 1/2 x squared and y equals x squared. Let's take a look at what happens when we change the a values into negative values. So I've started the table of values for you again. Negative 3 squared is 9. The negative of negative 3 squared is negative 9. That's 9 times negative 1. Remember, there's a 1 in front of there. And negative 2 times 3 squared. Negative 3 squared is 9. 9 times negative 2 is negative 18. So pause the video and complete the table of values. So with the table of values, I'm going to graph y equals x squared in blue. So here is y equals x squared. Next, I'm going to graph y equals negative x squared in red. Notice it's like a mirror image of the blue graph. And y equals negative 2x squared, again, is a narrower version of y equals negative x squared. So compared to y equals x squared, what happens to the y coordinates of y equals negative x squared? Well, if you compare the two, this is the same thing as multiplying each of the values by negative 1. And that's what gives us that mirror image. And if we do the same thing here, we can see this is multiplying all the y values by negative 2. So what happens to y coordinates? So compared to y equals x squared, the y values of y equals negative x squared are a times those of y equals x squared. And similarly, the y values here are a times those of y equals x squared. In this case, negative 2 times. It doesn't make a difference, whatever a value I choose. So for this one, it was negative 1 time. This was negative 2 times those of y equals x squared. If I was to graph y equals negative 4x squared, hopefully you see that, it would have to be inside the graph of y equals negative 2x squared, because it would be negative 4 times all those x squared values, which is what we call a stretch. So we can say inside the graph of y equals negative 2x squared. Example 1. Which parabola in the graph to the right has the greatest value for the magnitude of a? So magnitude means the number furthest away from 0, whether it be positive or it be negative. And looking at these graphs, you're going to look for the graph that looks the most stretched, or if you want, the narrowest graph, and that would be this one right here. So this graph here in green, that would have the greatest magnitude of a. which parabola would have the least value for the magnitude of a, so closest to 0? That would be the graph that would be the widest. So we can see here, the widest or the most compressed graph would be the one here I've highlighted in red. Which parabolas have negative a values? So those would be the ones that open downwards. So that would be this one here and this one here. So that's what I want you to know about a. The bigger the value, the more stretched or the more narrow the graph is. The lower the value or the closer to 0, the wider the graph or the more compressed. Positive a values open up, negative a values open downwards. So here's some new terminology. So a vertical stretch is a transformation that increases all the y coordinates of a relation by the same factor. And then a vertical compression is a transformation that decreases all the y coordinates of a relation by the same factor. So what does that mean? If you go to these graphs here, you see that. If you go to these graphs here, you see that starting with y equals x squared, this chart here, we see that compared to this chart, these values are getting smaller. So that's a compression. Similarly, these are getting smaller. So that's a compression relative to y equals x squared. Whereas with the ones we started with, if we compare to y equals x squared, these numbers got larger, so that's called a stretch. And these numbers were larger, so we call that a stretch relative to y equals x squared. So state the ranges of values that will cause the graph of y equals x squared to be vertically stretched. So to become taller, or if you like, narrower. And you notice for the ones that happens for would be a values greater than 1. Because remember, in this equation, this is 1x squared. So anything greater than 1 will stretch the graph. And if we want to write that mathematically, that would be a greater than 1. Vertically compressed would be a values less than 1, but greater than 0. Greater than 0. And that would be written as this, if you remember your inequality signs. And for reflected across the x-axis, that's the case where you get them opening downwards. So these would be a values that are negative. A values that are negative. And we can write that as a less than 0. Because anything less than 0 will be a negative number. So we're going to be able to graph parabolas using what's called a base table. So it says sketch the graph of y equals 3x squared by transforming the graph of y equals x squared. So as long as you memorize this chart, 9, 4, 1, 0, 1, 4, 9, we're always going to start with that. So let's graph that. And all our transformations will be based upon this starting blue graph, y equals x squared. So it says sketch the graph of y equals 3x squared by transforming y equals x squared. Y equals 3x squared is just a stretch of the blue graph. It's 3 times bigger. So all I need to know is that all these values will be times 3. I don't have to go and recalculate. I base it upon the fact that they're all times 3. So 27, 12, 3, 0, 3, 12, and 27. And I graph what I can. So I can graph 3, no problem. 12 doesn't fit. That's okay. We just graph what we can. So there it is there. So the green graph, I'm going to put a little legend here, is y equals 3x squared. So y equals 3x squared is what we call a vertical stretch of y equals x squared by a factor of 3. So that would be the wording we would use. We're sort of answering part C at the same time. It's a vertical stretch. And then we're going to do the second part. Sketch the graph of negative 3x squared by transforming the green graph. Well, if we look at the green graph, there are all our values, 27, 12, 3, 0, 3, 12, 27. All we're doing is multiplying by a negative factor. So this would be negative 27, negative 12, negative 3, 0, negative 3, negative 12, negative 27. And if we graph that, we see we get a reflection of the green graph. So that's the red graph. So we can add that to our notes. So y equals negative 3x squared is a reflection of y equals 3x squared across the x-axis. So a short question here. How can you graph y equals negative 3x squared by using the graph of y equals x squared? Well, the easiest thing to do is multiply. So we're going to multiply all the y values. If we want to do it in one step, all the y values of y equals x squared by negative 3. And if we did that, we can go from this blue graph right to the red graph. And we can say that the red graph is a vertical stretch by a factor of 3 and a reflection across the x-axis. So do two steps at once by just multiplying, and here it is here up top, multiplying all those values by negative 3. And eventually we won't need the tables. We'll just start with the blue graph and multiply all those y values by the a value. Example 4. Describe the transformation that was applied to the graph of y equals x squared to obtain the solid curve. So we're saying that y equals x squared. Hopefully you can see it as this graph right here. So how did I get this graph right here? What could I do? Am I going to stretch or am I going to compress? So since the blue graph is wider, we're going to compress the red graph to get the blue graph. But we need to know by how much. And all you need to do is find points on the graph and compare them. So for example, I can see here on the blue graph, I have this y value of 2. And on the red graph, if I compare the same one, so find ones that hit some nice numbers, I see there's a y value of 4. So when we think about multiplying or dividing, we can see that go from y equals x squared. So remember, we're going from y equals x squared. We're going to y equals a x squared, where a is the stretch or compression factor. Since we have 4 and 2, since red is our starting graph, to get the 2, we're going to have to divide by 2, or to get from here to here, we're going to have to multiply by a half. Right? That's how we get from 4 to 2. We can multiply by a half. Which means that for this graph, the equation is y equals 1/2 x squared. It's taking all the red points and cutting them in half. So this would be the equation of that solid curve, the blue one there.